Anyways, welcome to the first of our special topics lectures. This one is going to be on compilers before next week's, and by next week's I mean this Thursday's, on program analysis. I'm glad everybody can make it. I am extremely tired. I got here 3 hours ago off of red eye from San Francisco, but I flew back for the weekend to my work because we had a hack week this week, and I told everyone I'm going to be here today and then fly back because I got a class at 11 a.m. tomorrow. And everyone was like, stay, and I was like, no, I got to teach. So you're welcome. But anyways, we're talking about compilers today. We've done a lot of stuff with compilers in this course so far. We've gotten type error messages. We've gotten all sorts of crazy zany stuff from the SML&J compiler. And I've said a lot of random nonsense related to the compiler will do blah, the compiler is blah, as if the compiler is an anthropomorphic entity. Today, we're going to try and demystify a little bit what exactly the compiler is, so that you can at least think about it, if not implement it, okay? And I dare say some of you are ready at this point to try to implement a compiler now, if not within the next year, okay? Because the stuff that we did in this course exactly relates. But let's get started. So this lecture, like so many before it, is going to start with a story. And this story is a true story. It's also a scary story. But I'm going to pique your interest by telling you the story of the world and of programming languages. So here's where we are on the docket today. I'm going to tell you a story. We're going to talk about the theory of compilers and then how we can implement a compiler. And this is kind of like a rundown of the 12 weeks of content or 14 weeks of content you would get in 15.4.11, which is compiler design, which is one of my favorite courses at CMU. But if you like the content of this lecture, definitely take that course. But back to the story. So let's start, shall we? The history of programming languages. Well, actually, I had to look on Wikipedia for quite a bit to figure out this story myself. But let me tell you a story. So one day in the far, far past, a long time ago, programming languages were not real. Programming languages did not exist. And they were an idea, you see. People thought, what if I had, actually, most people didn't think, but some people, very smart people, were like, what if we had programming languages? But they still weren't real, okay? There weren't IDEs, there was no VS Code, there was no standard ML. I know, this is the horror part of the story, okay? And once upon a time, computers also were not real. Somehow that bothers me less than the programming languages part. But computers were not real. There was no Twitter, there was no hard drives, there was nothing that you could do. Everything you wanted to compute, you'd have to do by hand, by a simple machine. No calculators. You know, when the math teachers said, when you grow up, there's not going to be a calculator in your back pocket, like back then they were right, okay? But in this case, the history of programming languages takes us back to the 1800s when there was a loom, which is a thing that spins cloth of some kind, from what I gathered on Wikipedia. Okay, and it weaves a certain pattern based on punched cards that you would put into the thing. A punched card, a literal card with holes in it, punched, as like the one that you get at the yogurt shop on frozen yogurt place, the Froyo place. I can't remember the street's name, but like that place. Okay, for a discount. Okay, and this was an early example of what we could consider programming, which is I'm going to take this thing and then put it in and it'll adjust its behavior based on the data I put in, input, output, programming, okay? But then a little bit later, Ada Lovelace and Charles Babbage worked on something called the analytical engine. Raise your hands if you've heard of these people or that project, which is what we consider to be one of the first general purpose computers. This actually has very little relevant to anything I'm going to say today, but I want to give ups to my girl Ada and Charles. All right, cool. So we had these sort of like simple machines, but no computers. All right, but then by the end of the 1900s, this guy called Hermann Hollerith, with a very alliterative name, had this idea that maybe we could put data in a machine via a punch card and use it for data processing, like the U.S. Census, like keeping records, okay, and doing basic math. And he founded this company called the Tabulating Machine Company to use punch cards for data storage. And then he realized that name sucked, and then they became IBM, International Business Machines Corporation, which were big players in the original history of programming languages and computer hardware. Okay, massive players. A couple of decades later, this guy called Konrad Zuse comes out with something called the Z3, which is an actual programmable electrical computer, albeit still via this punch card idea. Okay, I have to keep a literal card. And let me walk you through what that looks like, right? So some people say, oh man, programming in SML sucks. All right, the error messages are terrible. I don't know what I'm doing. Why do you have to pick such a terrible experience for me to program in? You know nothing. I also know nothing, but from what I've gathered online, all right, we're going to put this scenario in your head, all right? So you're a talented programmer, in the 19th century or the 20th century, okay, and you're one of the first programmers ever. And what you do is you take these cards, this card stock, and you punch cards with them, or you punch holes in them via the special card punching machine. But it's all the way in the other room, and you got to use it, and you got to reserve that machine. So you punch some things, and if you make a typo, by the way, you got to start over. Okay, if you punch the wrong place, you got to start over. And then you finish it, and then you're like, okay, let me try to run my program. Well, now you got to walk all the way over to the other room where there's no air conditioning, stand in line, tap with everyone else who wants to run their goddamn code. And by the way, if you have like a stack of these, you have a stack of them, you have all of these cards, and if you mess up on any one of them, they're screwed. You're screwed. And if you drop the whole stack, well, there goes your week. All right, you got nothing left. I'll pick it up after the lecture. It's fine. No, you can't. So my point being, if you want to complain to me about Standard ML of New Jersey, all right, don't. But secondarily, also, this is kind of motivation for that. Okay. So point being, all the while I'm on the floor, picking up my punch cards, programming languages are still not real. Oh my God. That's the end of the lecture? No, not quite. So in the 1940s, now we could write programs in assembly language. Who's heard of assembly language? Raise your hand. Okay. Okay, and now put your hand down if you're not in 213 or have not taken 213. All right, great, cool. Which is like the barest machine code that can be understood by computers. You've probably heard computers only understand zeros and ones. That's kind of true. They only understand this thing called assembly language, which is very, very hard to read. And here's an example, okay? So like I might write an assembly-like syntax that's like add R1 to R2, and I compare on the result of that to 0. And if it's 0, I jump to 0x00067AB3EF. Otherwise, clearly I must go here. If I didn't go there, I go to blah, 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 okay? And the point is that this will be everywhere in your code, all right? And I'm sure some of you have read such assembly, okay? So this is what people were working with when they didn't have punched cards. That's okay. That's better. It reads like human syntax. That's cool. But what's the first thing I said to you on the very first day? We can do better. Let's do better. Let's program, but program better. So I'm going to quote Wikipedia here that I found online, but it was eventually realized that programming an assembly language required a great deal of intellectual effort. Citation needed. The only people that would put citation needed there are people who have never had to write assembly, okay? To be clear. So, don't trust Wikipedia, but what's the point? So programmers spend like hours, days, they pour over these cards, over these symbols, over assembly, and they want to write code, but they have to think about everything that's happened in the program up to this point. What did I tell you on the first day? Imperative programming, you have to think about the whole state of the program. Except now with assembly, you can't even have a good mental model of that. You have to know everything that's happening at every point. And if you make an incorrect assumption, there's no recovery from a typo. There are no type errors. God cannot save you here, okay? Assembly is no man's land. And still, programming languages are not real. But someone has an idea. Probably multiple people have an idea. Actually, I don't want to give you a conclusive, like this person did it first, because that's actually not very clear. But one person is John W. Backus in the 1950s, who was working for big IBM. And he was thinking, this assembly stuff sucks. This is terrible. I don't want to do that at all. What if I had a program that could take in, wait for it, text that's human readable in a programming language, he didn't use that word, and then it could turn it into assembly. And he called that Fortran. And by the end of the decade, he had implemented, along with a team of talented programmers, a program that could do exactly what I just said. And that was the first Fortran compiler. And then programming languages were real. And here we are now. All right, thanks for coming. So let's get into the theory now. Compilers, what the hell is a compiler? All right, so very broadly, I can explain it to you this way. A compiler is a program that translates data from one form to another. And that encompasses a lot of things. But usually when we say compiler, we mean a compiler that turns text in a programming language into some other form, but usually assembly language, machine language for a computer, on some kind of computer. SML&J, for instance, that you've been using all semester, is a compiler that takes in an SML program written as text, like in your IDE, and turns it into machine code that can run on your computer. Okay, and there exists numerous computer architectures. We're going to assume that there exists exactly one in this lecture. Okay, I don't care. Another idea that is kind of sister to that is an interpreter. An interpreter is something that takes your code and then it reads it and it executes it directly. It doesn't translate it explicitly to something else in the process necessarily, at least not visibly to you. Okay, so these are kind of similar ideas. And the SML&J REPL that you've used in this course is also an interpreter. Okay, but SML&J is also a compiler. And in SML terms, which I have to do, we can actually have a type signature for these things. So let's give a signature for what I'm talking about. Compile is a function, and what it is this is not going to be a very illustrative type, but it's a function of string to string. It takes in SML text, like programs, and outputs, like let's say assembly, okay? Some kind of generic assembly. And then also, we have this notion of run, which is a function that all computers can prepackage with. But it takes in assembly language, text, and it returns a unit because it just executes it directly, okay? So this would be assembly again. Right. Has anyone done the thing where you do like chmod plus x, like file name? That's what you're marking it as an executable, and then when you do // of that file path, you execute it. That's this. You're running it. You're running that thing as code. And also, we also have this idea of val interpret, where interpret is going to take in the original SML text, which is a string. So SML text, and it's just going to skip the nonsense and it's going to execute it directly. And what we should have actually is, ideally, we should have that interpret. And you didn't think this was going to be a 150 lecture, but actually I'm going to throw some 150 stuff at you. Should be equivalent to the composition of compiling and then running. Does this read correctly to everyone? Like, does everyone understand what I'm going for here? Yeah. In theory, at least. Okay. In practice, there's a few things that stand in the way of that. But this is the idea. Interpreting and compiling and running, very sister ideas. Okay. And that's exactly what I just wrote. And we should have this. Okay. But here's another way you can understand compilers and interpreters. I am second-gen Chinese. I always forget which one's which. My parents are from China. And I am a compiler for Chinese. Because when they speak Mandarin Chinese to me, I have to translate it in my head to English and then understand the English. Okay, which means that I have a lot of lag time. But I am an interpreter for English, which is my native language. So you speak English to me and I can just understand you off the bat. That's the difference between compiling and interpreting. Okay. So some of you are compilers. Thank you. One thing I always want to get across to people that I think is kind of interesting is this idea that a programming language, you can implement a programming language in that programming language. Raise your hand if this like makes sense to you. Because I think it's a very non-obvious sort of thing personally. Okay, too many of you are raising your hands. Put your hands down. I think it's kind of non-obvious. And partly it's because someone tried to explain it when I was like a freshman and they explained it to me wrong. And looking back like years later, I now know it was wrong and I know why I was confused. And now I'm upset about it. So now I have to explain it to you. So there's something called PyPy. It's a Python implementation written in Python. The SML&J compiler is written in SML. If you remember me complaining about the SML&J compiler, I was reading SML code for hours. Okay, it's written in SML, and the Rust compiler is written in Rust. It's a very common thing. Why can I do this? Well, you have to sort of separate this idea. So let me use some notation. We're going to say that compile subscript lang is a function of type string to string, which this iteration takes in code written in this language lang and outputs assembly. I don't know what this compile function is written in yet. Okay, I'm just saying that this is our notation for that specification. Okay, so compile SML is a function that compiles SML. Okay, but remember, a programming language is an idea. It's an idea in your head. Okay, before it ever gets real, before there's a compiler. So before John Backus was able to implement Fortran, he had this like syntax in his head. He had this idea of what it should look like, but nothing could understand Fortran at the time. There was no computer that could run Fortran code. But we had this crap on the board, on the ground. We had assembly, and it turns out that with assembly we can write any function at all. Okay, which means that, well, isn't one function this one? This is one such function. So if I have assembly, I can write compile _ Fortran in assembly. Now I have a Fortran compiler. I have something that can understand Fortran. Now Fortran is real. But using this, I can now use my Fortran code, my Fortran compiler, to write anything in Fortran, including compile _ Fortran. So my point basically being that before you can ever implement a language in itself, you have to have a compiler for that language. You can't go back for infinitely. But because we have assembly, we can code this. And once we have this, we can code compile Fortran and anything, including Fortran. I feel like I'm losing some of you. Yeah. Yes, that has to happen first. And now the computer is capable of understanding Fortran. Before you did that, nothing in the world other than your head could understand Fortran. But once you compile Fortran in assembly, now you can understand, the computer can understand Fortran. Now that the computer understands Fortran, you can write random programs in Fortran, like hello world, like quicksort, like compile Fortran again. You have to implement it twice. In assembly, must be, or something else basically, yeah. That is actually, I didn't necessarily say that here, but that is in practice what happens. That's called bootstrapping. If I brought Haichu today, I'd give you one. You can bootstrap a compiler by writing more of your compiler and using the parts of the compiler you already wrote. Yeah. Bootstrapping, because you lift yourself by your own bootstraps, right? Yes. Was that a question? No. You. Yes. There are things called assemblers, which can take assembly and like prep it for usage by the computer. But assembly is like very, very close to like the point where you can like execute it directly. Yes, I won't say that you can like execute it directly. Like assembly is still kind of a lie, but it's a very, very close lie. Okay. Yeah. Cool. Okay. I think this is interesting. It's not super important to probably what you came here for, which is how do I write a compiler? So, but I think that this sort of distinction between implementing the compiler versus using the compiler, it's a very important distinction to have in your head. Raise your hand if you feel shaky on this thing. Okay, either you're lying or you're all geniuses. Let's go. Either way, I win. Well, actually, if you're lying, I don't win. All right. Yeah, so this is actually exactly what I just said. Yeah. Okay. So PyPy, SML, and J, the Rust compiler, they all work the same. Guido van Rossum, bless his heart, had Python in his head in the 80s. I actually met Guido van Rossum. I got to present to him because I did work for Python, the type checker. But Guido, bless his heart, had this idea of Python in his head. It didn't exist. But then he took some language of choice and implemented compile Python in it. Let's say it was C, okay? And so he used C to implement a Python compiler. And then once he had that, Python was real. Computers could understand Python. So then he wrote Python code to compile Python. Yeah, that's pretty much it. That's all that matters. Okay, cool. That's all I wanted to say. That's compilers from 5,000 feet. Let's talk about how we are going to implement a compiler, and this will take the majority of the lecture. Okay. So let's say compile SML is going to be written in some language and have type string to string, where we take in SML text and compile it to assembly. Okay. Let's think about how we might do that. And the way that this typically happens is a compiler will take a program as a string and translate it through a bunch of different passes, a bunch of different phases, and it'll kind of like simplify and optimize along the way, which is how we get how powerful compilers we have today, where they can do, frankly, quite magic things. Okay, but we're going to go through exactly what those phases are. So, before I do that, though, why are we studying compilers in a class on functional programming, or rather, why am I talking about it in a class on functional programming? Well, I always say this. Even the most determined functional programming hater, okay, like someone who's like a complete like backwater, like they hate functional programming entirely, no, they cannot deny that functional programming is incredibly good for writing compilers. By the way, doesn't. He's coming to work at my company to do functional programming, in case you didn't know that. Okay, so I win. But anyways, it's very, very good for writing compilers. That's almost like its purpose. Okay, and partly because a compiler is just a transformation of data through a bunch of passes, right? And having typed guarantees of, oh, you can't mess this up, makes that process a lot easier, makes it nicer. And pattern matching and data type declarations, we're going to find, are essential for writing a compiler. If you don't have data type declarations, you're working like enums or something, you're going to cry. You're going to cry. If any, I have time for this. I'm going to say it. I was recruiting at Stanford like a year ago when I was in the Bay. And then I was talking to people, and what I do is close to compilation. So I asked them, have you taken a compiler course? And all of them, like invariably, they're like, yeah, like they kind of groan a bit. And I'm like, what? Why would you do that? Like compilers are so cool. What do you mean? I go and I look up their compilers course online afterwards because I'm a stalker. And then I find out that the Stanford compilers course is mandated in C++. And I was like, oh, that'll do it. I understand now. I understand the whole curriculum. So, no shitting on schools, but also, thanks. All right. So let's think for the rest of this presentation, except for the last part, we're going to assume we're implementing a SML compiler in SML. And I'm going to show you kind of like pseudocode, okay? We're not going to we can't go through everything because that would be incredibly hard. Okay. All right. 20 minutes. Compiler implementation. Well, what are we going to do? So most compilers have exactly the same structure, and it'll look like this. I have Lexing. What happens is I take in a program. Let me do this on the board, actually. So I start with a program that's like text, right? I start with a string, and I need to somehow impart meaning to that. So I take a string, and I turn it into something called a list of tokens. Basically, if I'm reading a program, if I'm reading human language, I want to kind of think about the parts of it rather than the individual characters. When you read English, you don't read like B-A-C-K. No, you read back, like a word, right? You read at the granularity of words. This is word separation in terms of programming languages, okay? Let's separate each thing into like a semantically meaningful token, all right? So this is called Lexing. The next step is called parsing. Parsing is where we take this token list and we turn it into a syntax tree. I may have alleged to this earlier, but programs are just trees, right? As you saw in your midterm one. So a syntax tree is what we get when we do parsing. And then after that, we translate it to, well, I'm not going to have room for this, but we're going to translate it to an intermediate representation, which usually takes some form of something that looks like assembly, but it's not quite all the way to all the stupid physical constraints of the real world, okay? And I'll elaborate more on that later. But we say like this is abstract assembly or intermediate representation. And here we do a lot of optimization. Most optimization in a compiler happens here. We stay in the IR for a while. We have a little self loop, and we optimize our code, okay? And then eventually, once we think we're ready, once we are finished with our optimization process, we say, let's go over to real assembly, okay? Which is itself kind of an arduous process. So these sort of phases, these edges I've drawn here, are kind of what is of interest to us, okay? And we'll go through all of those in tandem or in step, okay? And a nicer, as always, a nicer version of what I draw on the board is available on the slides. Okay, but let's start at the first step. Let's go back to the beginning. Lexing. How do we do Lexing? So again, words, right? If I want to read a program, if I want my computer to read a program, do you think I'm gonna case on hashtag #fcons, hashtag #ucons, hashtag #ncons rest? Is this how I'm going to write my compiler? No. Okay, let's try to do something better, all right? So generally the accepted practice is this is going to be our toy program for this first little part. And actually it's so important to have this up, I'm going to write it on the board. And while I write it on the board, I'm going to talk. I'm going to filibuster, because if I stop talking for a second, you're going to lose interest and you're going to get bored. But if I continue to talk while I write, you will not get bored. Actually, I read a story about a senator who read the entirety of Harry Potter on the floor because they wanted to filibuster. If you didn't know what filibustering is from social studies, it's fine. Anyways, I'm done with that. We tokenize this program. So instead of thinking about as VAL blah 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 blah, we're going to link them together. We're going to combine them, but separate them by the white space, because in SML, as we know, we don't care about white space in SML, right? So what we're going to do, I already told you that. So here's how it's going to look. We're going to color in almost every single part that's meaningful. So V, A, and L go together. One is it's a standalone, minus is separate. These parens are separate. And you see I've kind of colored them here by what they represent. Numbers are red, keywords are blue, regular identifiers that could be any name are green, and then syntax, equals and minus, those are orange. And there's a reason for that, okay? And the reason for that is because we're going to have to represent these tokens in SML. And in SML, here's how we might represent tokens. It's going to be a gigantic variant. It's going to be a gigantic sum type, okay? If I have a token, I might be holding a token that's val. I might be holding a token that's fun. I might be holding a token that's type. Or it could be an identifier, in which case, I don't know what the identifier is, but I've got a string along with it that explains to me what it is, right? Or I might have a number where the number is 1, 2, 3, blah, 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 right? Associated data. If I have syntax, I also have a variant for each of these things. You might seem exhausting for you to do this, but I don't know, for SML, there's probably not more than 30 of these. And that seems like a lot, but in terms of a language, that's actually pretty small. Okay, paying this cost up front by writing this code is going to pay off when we write our lexer. when we write our parser, actually. Okay. Do people see why like we could use this to represent an SML program separated by the white space? We're getting rid of the white space by tokenizing. Okay. I think people are good with this. Do you have a question? Minus. So this is a variant. So I'm saying that a token can be any of these things separated by bars. It might be val, might be fun, might be type. It also might be an identifier with a string attached, so on and so forth. Yeah, we say no strings attached, but in this case of id, that's not true. All right. Okay. So after that tokenization process, we get this. And here's why I picked the colors I did. I separated them by the syntax that they correspond to. So val's val. This should technically be id of string x, but I elided it because it gets really wide. I was trying to fit it on one slide. But this is actually going to be exactly the list that SML will tokenize to if in our Pro compiler. Okay, this rather, yeah. Because int, you might think int is a keyword, and it could be a keyword. There's a small syntactic difference though, which means that like I'm pretty sure we can use int for other things. Like if you can rebind the name int, but like a keyword messes up everything. Like you can't use fun as a name ever. This is kind of like a stupid, silly distinction I was graded on when I was in 10th grade computer science, but like it doesn't really matter. But there's a small difference between a keyword and an identifier. Yeah. Do people see why this, given the type on the previous slide, this is an SML value of a token list that corresponds to that? Cool. Okay. That was it. That was Lexing. I didn't show you how to implement it. It's boring. But we're going to skip that and move on. So parsing. So programs are naturally recursively defined, right? And some people like are always suspicious of that. So I do this. Okay, I say, do you agree with me? Do you agree with me that this is a program? Yeah? Yeah? Okay. Do you agree with me that this is a program? Okay. Do you agree with me that this is a program? Is this the I'm hearing yes. I'm hearing it. You're saying words. All I'm hearing is yes. All right. So anyways, this is a program. It's recursive. Deal with it. All right. All your programs are recursive. That's the whole point. Okay. If you could write finitely length programs, like what's the use? What is the use of you? God. My parents also yelled at me for being finite. Gosh. Okay. So anyways. Oh yeah, actually my example is funnier. If true, then big. Yes. Okay. Anyways, so this makes programs a great candidate for a recursive data type. So let's do it. Well, remember op trees? At least I'm sure some of you know op trees. We did RPN, right? And we avoided the tree part explicitly. But if I had an arithmetic expression, it might be corresponded to by this tree. And what is that expression? Can anyone tell me? What's that? Well, that was not clear to me at all. Actually, you need to audibly like. It's hard to express via. No, that wasn't. Okay, my practice is I say 1 minus 2 quantity plus 3, and that makes it like more clear where the delimiters are. But yes, life note for you if you ever need to explain something, like say quantity afterwards. Anyways, that's this. Do people see why? Okay, the plus is at the top because it goes last. 1 minus 2 happens first, right? The minus binds tighter. Okay, so that's that expression, and we see that this is just a tree. Yes. Wow. Arithmetic expressions are just trees. Well, what else could be like an arithmetic expression and then possibly be benefiting from a tree-like structure? Oh, by Jove, look at that. Programs. Well, the next thing I'm going to say is actually, this is abstract syntax. The difference between abstract and concrete syntax is in my thing here, I've got parens, yeah? But there, I don't have any parens. I don't need them because the parens here kind of indicate to me what the tree structure is. I don't need these parens to tell me because once I'm holding the tree, I understand that there are parens here, right? So I don't need the parens there. That's why this is what we call an abstract syntax tree. It's not a syntax tree that has everything that was in the source, but it conveys the same essential information, just in an abstract way, okay? So this is what we call an AST, or an abstract syntax tree, okay? What was that? Morphic? Okay, thank you. So the tree structure is what the parens were trying to hint at us at the whole time. So let's focus on the abstract syntax, okay? Concrete syntax is boring, right? Text is boring. But we can do something very similar to this op tree idea with programs. We're going to have an abstract syntax tree, which shows me the structure of this program. So for instance, this guy on the right here, this is going to be the same as the program on the left here. Val x equals that same arithmetic expression I just showed you is the same. Val dec is going to be a node of a tree where my left child is my pattern I want to bind to. In this case, is x. It's a blue box of x. And my right-hand side is, again, the op tree I showed you earlier. Well, it's kind of like a refinement of the idea. It's not too far from the op tree I just showed you. And again, like, what did we get rid of? We got rid of the parens because we didn't need it to indicate the meaning. We also got rid of the equals because the equals doesn't matter. Like, once we have the equals, oh, I understand. The reason why it's there is so I can know where my pattern and my expression begin and end. Okay, so the concrete syntax tree, boring. Abstract syntax tree, based. All right, we get this and we get rid of the equals and we get rid of the parens. All right. Does everyone see why like we don't need those things? Yeah. Cool. All right. You don't need them. You can move on. Okay. So for the running program I've got, which is that guy, we can get this tree. Okay. Here's the idea. At the top level of any SML program, I need a certain number of things called top decs, top level declarations. So I'm saying I have two. My first one is a val dec where my pattern is x and my right hand side is 2 minus 1. Yeah. And then my right-hand side, well, my next thing, my next top deck is a fun deck. It's a fun declaration. I'm using shorthand here. Where my name of my function is foo. The pattern argument I take in is a typed pattern where I type x at int, right? Sorry, that should be y, my bad. And then I add 5 plus x as the body of my function. But do you see why like all these components, foo, y colon int, 5 plus x, these are really just subservient to the greater fun declaration, right? Does everyone see why these are? Yeah. They are. Well, this is that doesn't even work very well because this is going to be a literal SML value in like a second here. Like the literal. Okay. Anyways, so the SML code, how we might represent that abstract AST looks similar to the C0 problem that was on your homework. It looks like this. And then I'm eliding a lot here. Okay, but here's the idea. An EXP is a type. It might be an int with an associated int. It might be an identifier with an associated string. It also might be plus of 2 expressions, right? A declaration might be a val dec, in which case it just has a pattern and an expression, right? A fun declaration is just a fun with an identifier, some number of patterns, right? Because I can take in any number of curried arguments. And then on my right-hand side, I have an expression here. And then a pattern can itself be like, just a string, or it could be a list of patterns because I have a tuple of them. Yeah. So do people see roughly like this kind of fits like your understanding of SML? There's some imperfections, but it doesn't really matter. The point is that we can write this structure, and this is a tree that denotes the structure of an SML program. And this is what we're going to parse to. I erased it. That's the thing that we're parsing to at the end of the parsing step. We translate it to this abstract syntax tree. Okay, but no equals, no val, no plus, I don't care. They're just there to get me to the right tree. Okay. The syntax guides me to the tree. Okay. Everyone cool? All right. And I will talk about implementation a little bit. An abstract syntax tree, we can get this via something called a recursive descent parser. Remember mutual recursion? Well, mutual recursion comes in handy for a recursive descent parser. It means that every EXP declaration pattern, all these types will have its own function. And its job is to parse one of these from the list of tokens. I'll show you exactly how that looks. So here's the idea. I'm going to have a parse pat, takes in a token list, and then munches off a pat from the front, and then returns to me the rest of the token list. I'm going to have parse exp, which does the same. It munches off an exp, and then returns to me a token list. Same with dex. Okay. Why does it return to me the rest of the token list? So I can continue. So I can keep parsing the rest of it. So if I had val x equals 2, when I call parse pat, I'm going to parse this guy with parse pat. And it's going to return to me the rest of the list of tokens such that I can get the equals, and then I can call parse exp on this guy as well. Okay. It's actually very much like the regular expression matcher that you saw. Remember, we bit off a string that corresponded to a regex. Similar things happening here, but we're biting off strings that represent programs or EXPs or PATs. Yeah.
Why don't we need the operator again, like equals?
So if I'm doing like a val declaration, like, do you care that the equals is there once you know that it's a val declaration? Because the val declaration, if you think about the information in that, I really just care, what am I binding? I'm binding this expression to that pat. I already know that I'm doing the equals because in the type, valdec is called valdec. It tells us we're in a valdec. But the pat and the exp aren't things that we can get from the name. I guess you could also say that valdec implies both of these things existing. So it doesn't really matter. Yeah, good question. Okay. Here's how the SML code looks. And it was a little scary, okay, but work with me here. Okay. Parse dec, we're parsing a declaration from the front of a token list. That means I case on my token list T's, I gotta give back two things. I give back the declaration I munch off, and I give back the token list. Well, if the first token is a val, doesn't that mean I should be parsing a val declaration? So if the first thing is a val, what do? That means I'm here. I'm here now. I'm here. I parse this. And now what is T's 2? This is T's 2. Yeah? And then what do? Oh, well, I got to get a pattern, but I don't know how long a pattern is. So I got to use my parse pat to parse it from here. But after a pattern, I always expect to see an equals. So I go and I use this expect function. It'll basically munch off an equals from the list. And all the while, we're getting newer and newer suffixes. Okay. And then I parse an exp, and I get T's 4. Okay. Basically, I'm saying, get this from the val, then I get T's 2, get this, and then get T's 3. Take this off, get T's 4, and then take this whole expression off and get T's. Maybe I was off by 1 there. Okay. But once I have the pat and the exp, I can put it into that variant I showed you, the valdec. And now I have my declaration. I'm holding it. And I have to give the rest of the list. Once I munch off everything corresponding to this val declaration, I have to give you everything that comes after. That's just my invariant. Okay, yes. Doesn't need to. Actually, I think cleaner if it doesn't. Yeah, separation of concerns, but good question. Yes. I think people are confused here. Please ask questions. Me looking on this side of the room does not indicate that I think that this side of the room is more confused than this side. Okay, to be clear. Yes. It says declare all these and then be that, return that.
And that's okay.
Yeah.
And
Good question. Yeah, and that valdec is a variant of the type dec. Yeah. Okay. Any questions on this side of the room? Yeah. We chunked it into bits for tokenization. But if I had like 2 plus 3 plus 4, in my tree, I want to see these together. We break them apart into tokens so we can put them back together at parsing. Yeah, we're stitching them together now. But good observation, like when I call parsing, it's exactly because this thing could be unboundedly long. It could be arbitrarily long, right? It could be 2 plus 3 plus 4 plus 5 plus 6 plus 7, so on and so forth, right? That's why you need to call a different recursive function, because that function, precondition or postcondition, it parses an expression. So once I get the expression, I'm done with the valdec. And then whatever comes next can be another declaration, maybe. Could be a structure, could be a valdec, who knows? But all I'm saying is that once I see a val, I'm hard committed to parsing a val declaration. Because what else could be next? That's the reason why keywords exist. Because once you see a keyword, you're like, oh, I see fun or type. I know what I need to parse next. It's to tell the parser what to do. Once you appreciate parsers, you appreciate why some languages have weird syntax, I think. Okay, yes. It's returning the tree corresponding to the expression, and then whatever comes after. Yep. Yeah. Okay. There was something I was going to say about this, and I can't remember. But this can look scary, but if you look at it, it kind of should just look like the declaration, like the structure of the syntax, right? What does the syntax look like? It looks like that comment I left up there. Val, and then a pat, equals, and then an exp, right? And that's what the code exactly is doing here. It says, give me a val, or it says like in a cheerleader voice, like, give me a val, give me a pat, give me an equals, give me an exp, and then it gives you back the tree. That's what it does. That's literally what the code is doing, okay? It reads naturally to me. It takes a little getting used to, but I'm going to tell you, like, this is very, very boring code, okay? So boring, actually, I have a different slide that says this, but most selectors and parsers nowadays are actually auto-generated. Like this code, you just write it. We've written programs that will generate this code for you from a specification of the language. So that's how boring this code is. Okay. No, don't feel bad about that. All right. You can call those Lexer and parser compilers. It's confusing. Okay. I should have showed you this earlier, but basically here's the idea, right? When I have a token list, which is it's going off a little bit longer, parse deck munches off this guy from it, but it stops right before the fun. It says, give me a val, give me a pat, give me an equals, and then parse exp goes a little bit farther. Then it stops right here. And then we iterate the process. That's all that's happening. Okay. Forgive me for spending a little bit longer on this. This is a large portion of what my work is. I deal with the front end of programming languages. So parsing, syntax, type checking, like all my jam. Okay. Okay. All right. Let's move on. So I have even more pictures I've neglected to show you. But parsePat gives me back this node with the X, and then parseExp will give me back this syntax tree of the equals, and I just stitch them together to return the final value of parseDeck, if you want to visualize it that way. My recursive calls give me nodes, and I stitch them together once I want to return. Okay. All right. Blah blah blah. Parsers are boring. That's what this side says. Okay. But once you have ASTs, you can do everything interesting. The syntax tree gets you away from the shackles, the fetters of the concrete syntax, because once you have a tree, you now no longer need to think about stupid things like, oh, is this nested inside that? Like, oh, should I visit this before that? Oh, is there a paren here? No, because the parens are gone. Only the bare meat of the program are left. So that means what we can do is we can write programs that transform ASTs to other ASTs or return things based on ASTs. Tree functions, okay? Compilation is nothing more than transformations and operations upon those trees, okay? For instance, what Zach asked about, type checking is a great one. Okay, so don't look at this. Don't look at this. Shh. Before I do that, look at this. I have a data type tie representing types. It's one of three things and possibly more. Ints, strings, and reals. These are constant constructors. Remember, I'm just using syntax you've seen before. Yeah. No. EXN is the only extensible type. That's actually literally something anyways. There are a couple of variants, including int tie, string tie, and real tie. Okay. If I wanted to type check an arbitrary expression that's like the one I showed you earlier, here's what I can do. EXP is a type with a bunch of constructors. I showed you like two. Here are the two. The other cases I don't care about. If I have an int, what is the type of an int? It's an int tie, right? But what's the type of plus of E1 and E2? What's that rule I gave you very early on in this course? I told you something like, if E1 of type int and E2 is of type int, implies that E1 plus E2 is of type int. Yeah? On the very first day, we did this. That's actually exactly what this is saying. It's saying that if I type check E1 and E2 individually, and both of them I get int tie, oh, that means the type of my plus must also be an int. Oh, but also the SML has a stupid thing. So I'm basically showing you into the SML compiler. This is a stupid thing I've been complaining about all semester. Something isomorphic to this, okay? And there's a line of code in there that does this, and it's infuriating, okay? Basically, it says, oh, also we can type check it at real and give back a real. Stupid. It's terrible. But I realize the syntax, like the data types are new. The syntax is old. This is just a recursive function on a tree, folks. All right? Yeah. No, we are currently verifying the types right now. Parsing is capable of parsing things like 1 plus high. It'll return to you an AST, but it's on us afterwards to look at this AST and be like, yo, what is it? You handed me garbage. What is this? Essentially, that's what this is doing, yes. Yeah. But the point is that if we can type check the whole program, we can attach the types to each node. I didn't show that here. Or we might just be like, yeah, looks good to me, and then continue on. Because once we pass the type checking step, we're like, good. No type errors. Yeah. Again, this is very much a toy implementation. I've simplified things very much, so I hope that you guys can follow along. Okay. But if you look at this recursive function on a tree, ints return ints plus returns plus blah 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 things. Yeah. Okay. All right. Let's move on. Okay. So type checking is just one thing we can do on an AST, but also some people do things like this. Some people do kind of silly things, and some of those people are some of us some of the time, but sometimes that's fine. Okay. And the point is this. What on God's green earth would possess me to write this? in my SML source. Why would I write this? Why should I write this? Yeah. That's the only reason I will accept. Why would you do this? I mean, like in general, if I'm doing this, probably what I could do is this. I could change my SML text to be this. Or my compiler could be a real smart homie and do it for me. Optimization. So and optimizing this is going to be just a tree transformation. So I want to turn val_dec of x equals, I'll read it out for you, okay? This is what it says. It says val x equals 2 minus 1, okay? I want to change this to val x equals 1. That's all I want, okay? How do I do it? It's called constant folding. I'm going to write a recursive function on a tree. Oh shit, okay, I have a lot of shit to say here. Okay. The point I was going to say was basically like, why should we simplify 2 minus 1? Because you're like, oh, it takes constant time, blah, 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 blah. Which is actually a good answer in this course. But in the real world, optimizations are going to add up, okay? If I can simplify an expression, that might lead me to further simplify expressions. Like if I can simplify 1 minus 2 plus 3, if I simplify this, now I can simplify this. Doesn't matter so much at the source text level, but at the assembly level, this stuff adds up, okay? Computers also repeat themselves like all the time. If you run a for loop, you might run it like billions of times. And if you shave off a nanosecond, that's going to add up. I don't know by how much. I can't do the math in front of you, but you're gonna get some amount of time out of it. Okay. Adjust the exponent by a couple. Okay.
Right. 1 second.
And if you have less operations, you have less bloat in your code. Okay. One real constraint is like the size of executables, and this was more of a problem back in the day. But you don't want to ship like a 10 GB executable. Okay. No one's gonna be able to download it. No one's gonna want it. Okay. If people won't even wait 200 milliseconds to look at your web page. What makes you think they're going to wait 5 minutes to download your file? Okay. So larger file sizes are bad, and also more instructions are bad. Okay, means you run less fast. So let's do some optimizations because it'll help us a lot. Here's how we might implement constant folding. It takes in an expression tree and gives me back an expression tree. Okay, if I have plus of 2 ints, and this must mean I have 2 ints, like int of I1 plus I2. That's what this means. I1 plus I2 must be what I just read in this tree. I turn it to int of I1 plus I2. If you believe me, this will type check. Okay. If it's minus, I do the minus. If it's div, I do the div. Okay, and this is how I simplify. Yeah. Usually yes. Yeah, we don't want to change it before we type check. Yeah. Is this good with everyone? Why did I ask you that? Why did I ask you if this is good with everyone? It would be if it wasn't completely, utterly wrong. Oops. 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 All right. Here's the problem. Well. This program can crash. If I'm trying to compile a program that has div by 0, right? I want my compiler to still let me compile it. It'll run at runtime, it'll crash. I don't want it to crash while I'm compiling it. My compiler should never crash. That's on me. So let's not do that, okay? This is unsafe. A compiler's job is always to terminate, always to give you an executable unless you do something dumb like don't type check, okay? But this is a perfectly valid SML program, right? Minus the other parts I need to make it a real SML program, okay? So what we can do is we can add in this clause here. If it's 0, don't do it. We guard the div by 0. All right, I'm going to give someone a chance to say what error number 2 is. Yes. It needs to call itself, because if I have something like, well, I think I'll give it a second. Oops. If I have something like this tree right here, this is minus of 2 things that are not ints, right? You agree with me? Which means that in terms of this function, where does that go? Wildcard. We get wildcarded out. All right, straight out. So what we need to do is we need to fold this guy and then fold recursively. So we're going to add this case in, and we'd actually have to do this for every single node of our syntax tree. Like if we had a bunch of expressions that are not these, we'd have to keep calling that recursively. I'm going to tell you right now, like in practice, there are techniques in functional programming that mean you write like not even this. Okay, you write very, very little. But I can't show it to you because this is kind of advanced. But we don't. I'm basically motivating you. You don't have to write this. But this is how we would do it. Okay. We fold our arguments. Okay, and we need to do it for every constructor in the EXP type. But this is how you write a recursive function that does constant folding. Okay, it's just a recursive function on the tree, and that way, when I write stuff like this, actually the compiler will understand that this is actually just 2. Okay. Any questions on that? Recursive programs, recursive functions. Yeah. Recursive solutions. Yeah. Because if I have a plus, these two things might not be ints, so I have to constant fold this guy first and call it recursively, because this thing you got to fold too. And that guy might have children that you got to fold, so on and so forth. You got to keep going all the way down, because with the program, there's no end. There's no stop. Not always. Other questions? And I'll make it through the high level. It's fine. Okay. So this is okay, but also like how many times in practice do people write this in their SML code? Okay. When they're not teaching 150, like not that often. So like this is kind of silly. Optimizations usually happen, I said, at the assembly level. So we're going to have to go there before we get any closer to this kind of thing. Okay. I spent a lot of time up here. I like it. We're going to spend less time here, but I'm just giving you the concrete idea. Okay. If you come out of this knowing like vaguely what a compiler does, I'm cool with that. I'm okay if you don't remember any of the code. I just want you to get the idea. Okay. So IR generation, we're going to go from the syntax tree to what's called abstract assembly. Basically, it's going to look like assembly, but we're going to assume we have infinitely many variables. In practice, we can't do that when we get to assembly, okay? But we're going to assume we have infinitely many variables, things called temps, places we can put data, okay? It's essentially a very, very limited programming language. So IR generation and then optimization. Let's do it. So abstract assembly looks... So for the rest of the lecture, we're going to be in a pseudo Python variant because it's actually very, very hard to describe what SML does because it offers us a bunch of nice things. And so I need to go to a language that has less nice things because it's easier to compile. But Python here, we have f, which takes in x, y, and then apparently x again. But that was supposed to be z. And it returns to me the sum of all these things. In assembly, here's how it looks. In abstract assembly, here's kind of how it looks. I have a temp t1, like a place, just a random name, and I assign it to y plus z, right? Because that's the first thing that happened. Then I assign t2 to be x plus t1, and then I return t2, yeah? The reason why I have to do this is abstract assembly doesn't allow nesting. We want to get as simple as possible, one thing at a time. So plus can't take in two expressions, plus can only take in variables. Plus can only take in like things that are already data, okay? This is just a restriction we're placing on ourselves because this is how real assembly looks. We're trying to get closer to assembly, so we have to unfold. And we'll notice that actually this makes our evaluation order very concrete. It says, first do y plus z, then do x plus that, then return that. If you squint your eyes and you're really on top of it, this should look to you like CPS. But if it doesn't, then that's okay. It took a few years for me to get it. But the point is that it should look very specific, like we're doing things very explicitly. Okay. One at a time, no nesting. All right. What was my footnote saying here? Okay, yeah. All right. I read the footnotes as I read my presentation. This is fine. This assembly here is fine for things called straight line code. Straight line code is where you don't jump around. You don't have an if, you don't have a while, you don't have any jumps, because it means that I just go from this to that to that. But how do I express in like linear order, like via a line of instructions? Things like jump there and blah without go-tos, okay? We're going to have something called a basic block. And let me draw you a picture because I think this is going to help. We're going to separately think of each sequence of straight line instructions as its own block. That means that if I have like T1 gets 1 plus 2, and then T2 gets T1 plus 3, and then ret T1, right? This was an uninterrupted stream of instructions. But if I ever have the case where I say, actually, like if T2 equals 0, and this is, I'm inventing syntax, there's two scenarios. Either it equals 0 or it doesn't. But I'm going to have to express that in my basic blocks. If it's equal 0, I go to a different block than if it's not equal to 0. Because this is a branch in logic. I can either go here or there. So I can't just have it be a block. Okay. This will make our reasoning simpler. It's called a basic block. And in general, this is called a control flow graph. Okay. Again, ideas. All right. So for instance, let's take this random function. Okay. F of x, if x is true, I return f of x again. Otherwise, I return f of not x. And yes, this loops forever. Okay. It's fine. I set x equal to true, and then I guns away. I go straight for it. What should I say about the control flow graph of this guy? Well, I think I'm not going to draw it out for you because I have better pictures. But here's the idea, right? When I hit an if then else, I have to branch. I have two possibilities, so I get two blocks. And when I eventually return from my function, I just end. But also when I call a function, that's also control flow. I call a function and I jump somewhere else, okay? So here's how it's going to look. And I've colored for you the constituent parts that correspond to each other in the hopes that this will make more sense to you. But my entry point is down here, right? Because I don't enter the function until I call it. I start up here. I say x gets, that's true. Sorry if it's hard to see. X gets true. Then I say y gets calling f on x. Okay. Then what happens? I jump over here to mystery land and I go to this orange block, which corresponds to my if. Now that I'm in the if, I use this command called CMP. It doesn't matter what it does, but basically I'm executing this comparison. If the comparison is true, I go to this red block. Otherwise, if it's false, I go to this yellow block. But also, oops, this should go back too. Both of these should go back here, basically. Sorry, there should be an edge from here to here. If I ever call f again, that means I have an edge back to CMP. I have to go back to the CMP. So in terms of like actually how I'm evaluating this, I say x gets true, I call it, I compare it. Then I go to the true case that's here. So I go here, and then I return call of f, so I go back. And it turns out actually I just stay in here the whole time. Okay. But in terms of the control flow graph, like we could conceive of a world where you could enter here if I called f with false. Okay. I'm just displaying how this stuff happens. I don't need you to get the motivation behind why we're doing this, but I'd like you to understand what, how it works. Yeah. Then what? This is just a different presentation of the go-tos.
Okay.
This way we can say like, a nice property is that every single instruction in a basic block, if you're in a basic block, everything else is guaranteed to run. Versus if I left go-tos, right? If I said like, blah, 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 go to A, blah, blah, blah. Now I have to like cut myself off before I get to the end of the basic block. We're just doing some pre-processing to save ourselves the trouble later, so that when I get to the end of this, I know, oh yeah, I have one out edge, I definitely go here. But here I have two out edges, so I have to think for a bit. I CMP to do it. Okay, this will make our analysis a little bit later, a little bit easier. Okay. But what's something that you notice about the CFG? Well, I kind of already pointed it out to you. Okay. Well, I pointed out to you the fact that we loop, but also this is true. Isn't it true that any way we go, we end up calling f? So like, even if it were true that like we inverted the thing here, it would still be an infinite loop because we always whoop, 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 because there's a missing edge, whoop, whoop, and no matter what, I always end up looping forever. That means that once we have this, it's actually quite easy to write a program that can be like, hey, this is an infinite loop. This is something you should not be calling. Have you ever done that in like a Python IDE? Like you'll like write like while true and it'll like gray out the rest of your text because it knows that you're in an infinite loop. And in fact, I would be surprised if it didn't do something that was pretty much just this. This is the simplest way to do it. Okay. Same thing with like a function that while loops forever, maybe it'll complain at you. It'll be like, oh, this function never returns. Okay. So this is the simplest way that we can do stuff like that. Okay. That's the whole point here. All right. So static analysis is easy. These are the two calls to f. We always end up there. Okay. Are people following me here? Okay. All right. But control flow graphs are also pretty handy because they let us know, even more importantly than when an optimization can be done, is more importantly, when can you not do the optimization? Because when does an optimization become not an optimization? When the compiler writer got too eager and moved something where he shouldn't have, or they shouldn't have, and then you messed up and you're doing this instruction when you shouldn't have had to. The problem with compilers is we have to produce an equivalent program. We have to produce always, in any optimization, any simplification step, the same program. If you change anything about the behavior of your program and your compiler, you're hosed. No one's going to use your compiler. I myself will write you an angry letter. Okay, don't do that. So let's look at another one. And I think this one's actually easier to understand, even though it looks scary. Here's the point, right? We're in the body of this function. Okay, we enter at yellow. I set res equal to 0, and then I have to go to the while. Okay, at the while, I compare res with num, and there's two things that can happen here. Or rather, there's one thing that can happen here. I have to enter the body of this, or I go, oh, yeah, two things, sorry. Either I return if it's false, in which case I go pink, or it's not true, or sorry, it is true, in which case I go here. Cool? And then once I'm here, well, I have another if. I check whether or not this number is even. So I have to compute it separately. I compute res mod 2, and I check whether or not it's equal to 0. And if it's true, I go orange. Otherwise, if it's true, I go green. Okay. And then once green and orange finish, I'm in a while loop, by the way. So I gotta go back to blue. I gotta compare this guy. Okay. Does that intuitive explanation make sense? Like I'm reading to you what this code does, but reading what that code does also induces this structure here. It tells us this is what the code's really doing. And depending on like deciding which edge that we pick, like I don't care about that. Like don't concern yourself with that. Okay. But this is what the graph looks like. Okay. Cool. One thing I'm wondering here is what can we optimize here? Anyone have a guess? What's like a big computation I'd like to potentially optimize? What's something I'd like to optimize? Maybe is a better question. Like something I'd like to not do a bunch of times. Imagine this while loop runs like a million times. Yeah. Store res mod 2. Yeah. But except for the fact that res is being changed.
Oh.
So here's the thing, right? Yeah, exactly. This control flow graph is going to be very helpful for us because you might think, let me store the res, and if you move the res up here, well, now you've got a wrong program. You've done something different than what the original program said. So the real reason we have this is so we can know when is it not safe to do this optimization. What I had in mind was basically I wanted to move this guy up 20 times num because I don't want to keep multiplying by 20. Also, the num I'm pretty sure doesn't change. Yeah, it doesn't. Okay, so I have a few candidates here. What if I wanted to optimize out this guy 20 times num? Well, I have a few choices. I could insert it out of the function entirely. Could I? Why? That's out of scope now, so I can't put it there. Okay, so junior compiler writers, we're figuring it out. We can't put it there. And why did I write that out? I don't even know. Oh, that's probably a mistake. I don't know. I made it this morning. Otherwise, I could put it here. Are we good with this? So instead of I made this temp, this is red for probably no reason. And I made this temp equal to 20 times num. Is this cool? I hear okay. Do you think this does the same thing? Oh, sorry. Yeah. So before this yellow thing, this is where it was, right? All I've changed is this yellow stuff. We can move it here. Does this do the same thing?
Yes.
That's a separate question. Then is it good? I agree with you. It produces an equivalent program, but I don't know if this is what we should do. Why? Can someone give me a reason why we might not want to do this? Yeah. I'm doing this kind of like in intention, like we're going to do this by the assembly level, so we don't have to worry about that. But that's kind of related to what I'm thinking about. Why is this unrelated? What do you mean by that? Unrelated. You said this temp is like unrelated or collides or something. Create a new variable. Sure. Okay. Yeah. I'll take one more. Yeah. Yes. Can you tell ahead of time just by looking at this whether or not we really entered this case or this case? I don't know. If you looked at this long enough, I cooked up a random example. Maybe you could figure it out. Okay. But the point is the compilers aren't smart, but they're not that smart. If I do this up here, yes, it'll be the same program, but I also compute 20 times num even if I always go in this case. If my function always goes in this case, I'm going to always compute that 20 times num. And sure, in this case, it's a constant thing. Like maybe it doesn't matter that much, but this can matter. Okay. Do you have a question? Okay. This is a contrived example, but there are a lot of examples where this will matter. Like if you hoist too far out of your loop or out of your function, you're going to introduce extra cycles because you don't have magic eyes. You don't know that this always happens. So in terms of the control flow graph, like what this means is basically like, what happened is that we moved this, where did we move it? We moved it, I think here, pretty much. We moved it like before this, okay, before the CMP. Except that now this thing is here, which is a different path than this, right? Here is a different path than here. Blue, red, green, okay? Blue, red, green is different than blue, red, orange. So people see what I'm getting at, like, sometimes that's no bueno. Okay, control flow graph will be your friend. It will tell you how we do this. We do this by a very classic compiler technology called data flow analysis. If I have time next lecture, I will describe it to you, but it's kind of involved. Okay, but yes, all you can trust is that yes, we can figure this out. All right. Okay. Why the hell did I do this? Oh no, this is a different thing. Okay. And also I have another question, which is like, if we hoisted it out here, what if it was div? What if it was div? Can I do that? Is this the same program? Does this do the same thing? If it was multiply, it would be the same program. I agree, just maybe less efficient. But also, if this was div, yeah, you're hosed. You can't do that because why? What if num's 0? What if num was 0 and we always entered this case? We would never compute the div by 0, we would return, but here we always div by 0. Okay. Compiler writers have to think a lot about this. They have to think about like, what does it mean for a program to do the same thing? It's easy for this example, harder when you have like a bunch of random widgets in your language. Compiler people are pretty smart. So compiler optimization is interesting because you have to always preserve equivalence, but you have to make sure you don't change the behavior. Here's a kind of a check your understanding. I don't think I'm going to check it now because I feel like saying other things. Okay. I already said this thing on data flow analysis. Okay. All right. With CFGs, optimizations are just easier. It's really easy to say something like, oh, this value will be used everywhere from here on out. Therefore, it's okay to like optimize up to here. Or it's really easy to say, oh, there's a path along here where I don't use this variable, so I shouldn't move it here. Okay. These are the kinds of questions we usually ask with control flow graphs. Okay. That's the whole point why we have them. All right. And then I'll also give you some vocab. This is not super important, but local optimizations, we call those optimizations that work on just a block. So for instance, if I had like 1 + 2, even here, I move this to 3, right? And maybe I also move that, okay? That works within a single block of straight line instructions. I don't need any knowledge of how the functions go. I don't need any knowledge of how it loops. I can just do it here because it's always better, because I can always make this 3, that's fine. A global optimization is an optimization that you have to like look around your graph. You have to like look at everything. Those are harder. Those are way harder because that introduces a lot of cases, okay? So those include like dead code elimination. The thing that Python does where it grays out your code when it knows that you can't reach it. That's like it's not an optimization, but it's an interprocedural analysis. Okay. Unused variables is one. I have to look at every single path from me and see that like, oh, wait, none of them are using my variable X. This is a very classic thing that you should have in your IDE. If you don't have this, life is pain. And function inlining, which I don't feel like talking about. Okay. Thumbs up, thumbs down, thumbs minus. Where is everyone with me right now? More people, come on. All right, now let me do an experiment. So can everyone like hold their thumbs up like as wide as they can and just like even if you don't, yeah, can you just thanks. Okay. Okay. No, I didn't. You didn't have time? Those things because it was yesterday. Wait, okay, look, this is more important. This is more important. Have I taken my B-roll?
And Brandon's B-roll. Yo, huge.
Thank you. All right, thank you. Good suggestion. I would give a high two. I would give a high two for that one. All right, we're almost at the end. We're almost at the end. Okay, we're actually like pretty much just at the end. Okay, a lot of crap happens here. There's like 2 kinds of people that are interested in compilers. Okay, you have programming language people and you have systems people. This is actually a massive political like thing in the department. Don't tell anyone I said that. But well, it's not a secret. But the point is, the systems people are all here. They want to optimize for certain architectures. They want to do really cool things where they make the assembly instructions take less time and take less space and be more efficient. I am a PL kind of person. I work up here. I like type checking. And this might seem boring to you, but there's a lot of cool stuff you can do with the semantics of the program when you stay at the level of the source. That's actually what I do for work. That's unrep. But yeah, here code gen is also kind of pretty well defined. Okay, we'll see what we do. So we're at the abstract assembly. We did a bunch of optimization, and we have assembly that we are fairly sure is equivalent to the original program, but it's smaller. Now I got to make real assembly. How do I do that? Okay, well, here's how I'm going to have to do it. Abstract assembly, I told you, assumes you have infinitely many variables. Whenever I have an intermediate computation, I call it T1 or T2 or whatever, right? I can just do that. Computers don't have an infinite amount of memory, okay? And computers have even less memory that's like fast to use, okay? There are certain locations around your computer's CPU that need to be used to make sure the operations are very fast. There's like 8, 10, 20 of them, okay? So if I want to make sure my operations are very fast, I have to make sure I'm using those as much as possible, okay? So this is the problem called register allocation. It's very, very far beyond the scope of the course and my ability to explain to you, but I will give you an analogy in a second, okay? But the idea is basically just like if I tell you like I want to put this in, they're called registers. I want to put like my data in some register. At some point, I no longer need that data, in which point someone can overwrite my data. But it's a whole like synchronization problem where I need to make sure if I put my stuff here, I know exactly when I need to overwrite that data, and I'm overwriting optimally. Like there's a register called R1 maybe, okay? If I'm putting like random crap in here, okay? If this is here until the end of my program, I probably have done something stupid, okay? Because I should be hot swapping with these guys. Because the reason is that certain locations, these registers are really friggin' fast. They live right next to the CPU, and then main memory is like all the way in Texas over there, okay? So it takes a long time. So this is the systems level of the thing where, like, principally, I tell you, I don't care about this, but it does matter. Right? Here's an analogy for you, all right? I know you love analogies. I am really popular. I have a lot of friends, okay? And it's my 8th birthday party. And I only have 8 seats at my birthday party at Chuck E. Cheese's. But most of them hate each other. How do I make sure that all my friends can go to my birthday party without, like, well, first of all, killing each other. And second of all, they're only available at certain times. My friends have busy schedules too. They're 8-year-olds. They're too busy learning function composition. And if they're not there for the full time, they're going to get angsty. They're going to get really mad. If they're like, I'm available from 2 to 5, and I put them there from 2 to 4:59, they're going to get mad at me. I got to make sure they're there for the full time. Okay. This problem of scheduling, like, oh, you can come in at this time, and then, oh, but this guy leaves then, and then, oh, there's a seat open now, and then you can come here. Oh, but you won't be here for the full time, like, so maybe I won't put you there. That's register allocation. That's the problem. And you can imagine it's a big planning problem, okay? If you know the term NP complete, it is NP complete, yes. Yeah, more specifically, this problem is one called graph coloring. If you have a graph, how many colors can I assign such that no 2 colors are next to each other? Okay. Take 251 for more. Okay. I didn't sign up to teach you theoretical computer science. I signed up to teach you functional programming. Okay. Yeah. How do I plan a schedule such that every friend can come for the full time they can, and I want to maximize their and my happiness? Everything de-sugars to a happiness problem and a graph problem. That's their analogy. I can't explain it any further. Yes. No, definitely not. Because consider I have 8 registers, and then I have 9 variables, and all of them live for the entire duration of the program. They go to Texas.
Oh, okay.
They go to Texas. I take my parcel of, like, my little data, and I'm like, sorry. In terms of the birthday analogy, I tell Timmy, like, you can come. We got a voice in. You got a Zoom call me from Texas, and I ship him out. And then 500 milliseconds later, he's over here and he calls me, and he's not happy about it, but at least he got to go, right? Yeah. No, the problem is I had too many friends. If I had 7 friends, I'd be okay. They all get a seat.
But like now you have some.
Oh, sure. Okay. Fine. If I had 10 friends, like, yeah, two of them might have to go to Texas, but it's not always guaranteed they have to. Okay. This is like pretty much exactly what's happening. Okay. We go to main memory. We go take like 500 milliseconds, which is a long time. Okay. Good question. Give me a good analogy. Cool. I didn't even prepare for that. Awesome. Do you see my joke? Okay. Okay. Oh, there's a problem called all available.
Oh.
You try so hard. Try lambda when to meet. Yeah. Okay. Okay. After a lot of index cards and going to Texas, a surprising amount, we're at the assembly. Finally we have the real assembly from the abstract assembly, and we can run the executable. Story's over. We are finished with the compiler. This is like the 5,000, like 5-mile up view of what a compiler is. Okay. A lot of parts of each phase have a lot of nuance. Mostly the fact I didn't show you any real code that runs. Okay. But the intuition, I hope, is what gets you, right? What I want you to think about is this. Burn into your brain. Blue, green, purple, red, yellow. Okay. It's graph colored. What do you want from me? Okay. No, not the colors, but well, that's optimization. You get to do that. Yeah. My point being, compilers are magic. Okay, I've said this a lot. I'm sure you know compilers are pretty magic, but now they're a little less magic. Okay, you should know like what your program looks like. All of this is subject to these constraints that a lot of smart people have thought about. That John Backus back at IBM in like the 1950s was thinking about when he wrote that Fortran compiler, and he lugged it uphill both ways. So what I'm trying to say is, if you have the bird's eye view of the compiler, sometimes that's all you need. Once you know how a compiler works, you can become a better programmer, better software engineer. This is not the end. I have something else to say. Functional programming is good for compilers. I said that to you. I didn't spend a whole lot of time motivating it. I kind of like said a sentence or two, but I wanted to recap here. But like, yeah. Simulate a C dot interpreter. What do you mean imperative thing? If your language has imperative features, at the source level, functional and imperative is something we only use to describe things, living up there at the language level. Once you get to the assembly, everything's physical hardware. Yeah. Abstraction, again, abstraction, we invented it so it could serve us. I live up here in abstraction land. People down there are manning the trenches. Okay. Okay. But yeah, any other further questions? I'm about to wrap up. Okay. Last thing I want to say, basically, I want to motivate you. Functional programming is good for compilers for a few reasons. Okay. Compilers, again, I said this a couple times. They're just tree transformations. I promise I won't ask you a question about it on the final, even though it would be totally valid. Okay. Compilers are just really fancy tree transformations. We run functions on trees because programs are trees and trees are our happy place. Okay. For functional programmers, we're very good with them. And also, compilers cannot be wrong. The day that a compiler is wrong, society shuts down, and I swear to God, I swear to God, there should be no programmers left. Okay, if you compile your code, and you can't trust it, that is the doomsday scenario. No hope at all. Society is done. So we got to write a compiler that works. What's that thing I said on the first day of class? We're not in the interest of writing code. We're in the interest of writing correct code. Okay, that's what we're here for. So compilers cannot be wrong. Type checking, algebraic data types, data type declarations like you saw in this class, all of these contracts that are enforced by a functional language ultimately help us when it comes to writing a compiler. 2.5, which I haven't put here, is that functional programmers are language nerds. Like PL people are functional programming people. Therefore, compiler writers are usually functional programming people. That's not like meta reason. And then finally, compilers are pure. If I give you like a program, an input program, any input program, I expect you to get the same AST with the same input. I expect you to get the same list of tokens out of the same output. And also, I kind of expect you to optimize it the same way. Because what if you optimize it differently? Well, now 2 runs might be different. And if you write a bug, now I've got a non-deterministic compiler. I've got a compiler that doesn't work. And which means I don't have a compiler. I have a piece of junk that I spent $5,000 for. That's very little for a compiler. Okay? Yeah. So okay. The simplest way to describe undefined behavior in the language of like C, like, oh, this program's undefined behavior, is that the compiler writer got too lazy and they didn't want to define what it would do. So they just said, yeah, up to your interpretation. It's failing a precondition. Same way that fact is allowed to do whatever on a negative input. Compiler is allowed to do whatever on an undefined input. That's the whole reason. The only reason is just because they didn't want to define it. Maybe it was too hard. Maybe it was just not worth it.
So it's just like a missing case in like.
Exactly. Yeah. It's like a pattern match with the missing case.
Oh.
Exactly. And they tell you, oh, if you run into the missing case, that's your fault. Undefined behavior. SML doesn't have undefined behavior. Okay. Oh, wait, I was going to show you this hilarious thing. About that. Anyone remember this from Piazza? Sonia posted this hilarious thing.
Hey, yo.
Remember the thing I said about register allocation? Boop. This is a compiler bug. I just feel like showing it to you. Yeah, they're trying to choose the victim for the register allocator and it's done. Anyways, I'm almost done. No immutability needed. Deterministic compilers, functional programming. I hope this helped you understand compilers a bit. I have some new questions on this I'd appreciate if you'd answer. Okay? Thank you. Thursdays will be even cooler. Thank you.